Hi everyone, my name is Matej. I'm one of the founding engineers of Protokit, and today I would like to introduce you to the Mina ecosystem in general, and also to how you can utilize Protokit to build faster on the Mina protocol. First of all, check out all of our socials. So you have the Twitter at the top, our Discord in the middle, and the website at the bottom, where you can find all the relevant docs in case I miss something during the talk. So let's get started. Every time I try to explain a certain concept, I like to start from the basics because I believe it makes understanding the more complicated stuff a lot easier. So let's start by going from zero to ZK Hero and learn everything that you need to be building with zero-knowledge technology. First thing you need to understand is what is a ZK proof. So ZK proof is a proof of computation in a mathematical sense, done on top of using private or public inputs. We have public or private inputs, but we also can have public outputs. So you can think of a ZK proof as some sort of a function, could be a programming language function that takes data as an input, does some computation, and provides data as an output. The things that you can be computing within your zero-knowledge proof might include things like signature verification, Merkle tree inclusion, hashing, and all sorts of different things. If you want to compute a proof, you first need to implement your program that's going to represent what the proof is proving. To do that, you need something called a proof system. You could compare a proof system to, let's say, a compiler or a GVM engine or something like that. The engine or the proof system that we use is called Kimchi, and it's the same proof system that powers the Mina L1. Computing a proof is a result of something we call a circuit. So you have to execute or run a circuit, and that's going to give you a proof. Circuit is a set of something we call constraints, which are programmable rules for the proof system that then determine what kind of things are actually being proven when you execute your program. Once you have your program implemented and you want to start using it, the first thing you have to do is you have to compile it. And the artifacts of like normal program compilation, usually it's a binary. In our case with circuits, the artifacts of compilation are prover and verification keys. The interesting thing about proofs is that once you implement your program, you generate your proof by supplying arguments to the function, then takes a couple of seconds, you end up with a proof. The important thing to understand here is that the computation of the proof usually takes a lot longer than the verification does, and this allows us to build some pretty interesting systems like ZK-powered blockchains, which help us innovate over like traditional blockchain designs. So once you get a proof, you can take the proof and verify it in a matter of milliseconds using the originally generated verification key. Why do we even call proofs zero-knowledge proofs, right? So the proofs become zero-knowledge when we understand that a subset of the inputs that we use to compute the proof can be kept private or not exposed to the person who is then verifying the proof. So you have two parties, one is doing the proving, one is doing the verifying, but only the proving party knows what exact data the proof is computed on top of. That is one of the important things here. Within the Mina ecosystem, we have this really amazing DSL called O1JS. We call it a ZK DSL for writing circuits. The program that you see right here is a very simple counter implementation that keeps de facto like a private state, and the private state is always a hash of the count where the counter is. So going line by line, the DSL allows us to implement our program, our function, which is going to be the method at the bottom, but we first have to provide some metadata for the circuit itself. We have to provide the type of the input and the output of the program. In our case, that's going to be something we call a field, which is the most fundamental primitive of the proof system itself. It's a number that is sized somewhere around 255 bits, and we will do most of our computation on top of fields. So how the counter operates is that As an input and output, we have a single field, which is going to be our counter, but it's not going to be a raw number. It's going to be actually a hash of the number that we are keeping track of in our counter. That allows us to keep the counter private, but also ensure that we are incrementing the counter using the given set of rules that the program specifies. So what kind of rules do we have for incrementing the counter state? So apart from the public input and the output, we also have private inputs. That's going to be the variables A and B. Those are the ones that are not going to be exposed to the person verifying the proof. That's going to be resulting from executing the increment method of the counter program. So going from line 10 to line 13 in the method implementation, the first thing we have to provide is the public input, and then the two private variables, A and B. The public input is the hash of the current state of the counter. A is the pre-image for that hash for the public input, and B is the number which we want to use to increment the counter itself. The first thing we have to do in this code is we have to verify that whoever is running this counter knows the pre-image of the current public input or the current state. Therefore, they are eligible to use the counter and increment it. How can we verify that you know what the private state of the counter is? All we have to do is provide the pre-image, hash it within the circuit, and then do an assertion right on the line below to the public input, which is the original hash that is like publicly known. Once these two hashes equal, it means that you knew the correct pre-image, and you can continue in the circuit execution by incrementing the pre-image with the number that you want to add to the counter, and then return back the new state, which is going to be a hash of the incremented counter state. So we went from one hash to another, and in between, we've done some addition. That is what a counter circuit does. If you want to run the circuit, first you will have to compile it. That gives you the program verification keys. And then let's assume that this is a unit test for the circuit. The first thing we have to do is we have to define the initial state. That's going to be a 0. Then we have to define the public input, and that's going to be the hash of the initial state. And then the third variable, by, is the number that we want to be incrementing the original state by. So line number 7, we actually get to run the circuit. And as a return of that execution, we get the proof of executing the increment logic correctly. So we provide the arguments. So we provide the original state that everybody knows. That's the public input, which is the hash of the pre-image. Then we provide the state, that's our pre-image. And then the number we want to be incrementing by, that is the third parameter. The result of that asynchronous call is a proof computed by the proof system behind the scenes, which the DSL gives us a really easy access to. Going on then to lines 10 and 11, we can inspect the result of the execution by inspecting the proof. We can take a look at the public input, the public output, and that gives us the hash of the state after we have run our circuit logic. That means a hash of the original state plus 1, since we were incrementing by 1. This is something that the person who wants to change the counter state would do, and then somebody who would like to verify that the increment, that the state was incremented correctly, they can take the proof, as we can see at the last line, and they can verify the proof and ensure that the person who was incrementing the counter did it correctly, plus they knew the original state, and they have not done anything else with the number that they were not supposed to be doing. So that's like, TLDR of how proofs and circuits work, and also how O1JS allows you to interact with the proof system to tap into this amazing technology. Another interesting aspect of circuits and proof systems is the fact that the proofs or the circuits can be recursive. So that means that you can have two separate programs, one responsible for the counter incrementation and another one responsible for authorizing that you are a actual real or a valid user that has the permission to do something to the counter. So at the top we have like a mock ZK program that defines a credential proof, and we can extend our counter program with a new private input, which is going to be a proof or the credential proof. And then at line 16, we can verify the proof within the circuit itself, and that is how recursive proofs can be used to compose logic of multiple different smaller circuits into bigger chunks. This is a very, very important technique that unlocks a lot of new interesting designs that wouldn't be possible without proof systems themselves. So how do we go from circuits, proofs, proof systems to something more interesting like blockchains? Normally, like a traditional blockchain is just a spicy distributed database that has consensus on top. Nodes execute user transactions, and the transactions are authorized intent to perform some sort of an action on top of the chain state. Once the block producers take the transactions and produce blocks, you end up with like blocks, right, that are propagated through the network, etc., etc. If you are participating in a traditional network, let's say Ethereum, you are a node operator or a block producer or whatever you would like to call it, and you want to verify a block that derives to your nodes over peer-to-peer. To verify it, you have to re-execute all the transactions on top of the original state to verify that the block is executed correctly and that the state is correct. If you want to do this, you usually need some sort of beefy hardware, right? This makes it difficult for the chain itself to decentralize, since the barrier to entry is like very high or expensive hardware. What Mina does is fundamentally different in a way that the whole block production process, consensus, and everything else required to operate the chain and produce blocks, apply transactions, so on and so forth, is implemented as circuits. That means that everybody, like everyone who's participating in the network, either like full nodes, light clients, or others, they don't have to reapply the transactions again to verify a block. All they have to do is they have to verify a proof. And this like relatively innovative approach allows us to build a network that is, let's say, cheaper to operate, and it's easier to decentralize. Thanks to the fact that block production now results into a single recursive block proof. All right. So that was like basics of chain design using circuits or zero-knowledge proofs. And to ramp it up, we also need smart contracts, right? Like, what use would it be to have a chain that doesn't have contracts, and you wouldn't be able to have programmable logic on the chain state? So Mina has native smart contracts on its own L1. And the smart contracts are also implemented using the O1.js SDK. There's this smart contract primitive that you can use. It's all in TypeScript. It can run in browsers, which is a very important aspect. Smart contracts are, again, only circuits that can improve their own executions. They are executed completely off-chain, or another way to say it would be they're executed on the client side. You can think of it as being executed literally in your browser. And this allows us to keep the node hardware requirements for L1 block producers to the absolute minimum. As I've said before, in like traditional blockchain designs where the smart contracts are executed on chain, the transactions are just signed intent that tell the node operator, hey, please execute the smart contract method with these parameters and tell me what the result is. On Mina, the story is entirely different. Instead of the transactions, tell them, like, you want to run a smart contract transaction on Mina, you will run a circuit off chain. The result of that circuit execution is going to be a list of instructions for the chain on how it's supposed to be updating its on-chain state. We call these instructions account updates. So yeah, those would be the account updates. The account updates need to be authorized so that the block producer can provably verify that whatever instruction they received in the transaction can be applied validly to the chain state. So these account updates can be authorized either by user signatures, which is like a very simple case, or by proofs of the smart contract execution. So yeah, the block producer only verifies either the signature or the proof and applies the transactions to a database. And again, the block production process, or applying the result of the execution of the smart contracts, results into a block proof. There's one downside to this approach, and that is that there's a potential for race conditions. Since imagine like there's, I don't know how many people here in the room, and all of you would like to interact with the same smart contract, but you're all proving on top of the same data on your own devices, and then you all send the transactions to the node. And when the node is producing a block, it has to discard certain transactions because they were done on top of the same data, but the chain data has already forwarded its state because one of the earlier transactions was applied. So there's no built-in way for users to organize off-chain to prove the contract execution sequentially on top of changing data. So here's how a smart contract looks like. It's very similar to the raw circuit that we saw before. It also does the same thing as the circuit that we saw before, the counter, with one difference. We have on-chain state. So instead of storing the current counter state in a public output, we store the data on-chain, and that it allows us to do the same kind of computation, verifying the pre-image, incrementing the number, and storing the result on-chain as well. This is how you can interact with the contract. There's a simple API. You send a transaction, calling your contract, you prove it, you send it, you end up with a list of account updates. They have certain parameters, preconditions, which is the commitment to the data that you computed on top of. That is the race condition problem that I was describing, instructions to update the state, and the proof authorization. This is roughly a life cycle of how the contract operation works. Alice executes the contract on their client, produces a list of account updates, proves the contract execution, sends that to the block producer, and eventually when the chain produces a block, you go from an initial state to the resulting state by applying and verifying the account updates. So that's roughly how it works with the smart contracts. There's one caveat with circuits that I haven't mentioned yet, is that all circuits have to be constant size. That means that you cannot do stuff or like computation on top of dynamically sized arrays unless you employ some fancier cryptographic techniques that allow you to do that in a provable way. This also means that the smart contracts don't allow you, by design, to store key value pairs in the chain state. So in this way, you could say that the smart contract API is relatively low level, and it's up to you as a developer to figure out how do you want to service your users when it comes to, let's say, off-chain storage or transaction sequencing. So instead of storing key value storages, you can store a commitment to some cryptographic data structure that then allows you to prove that whatever data you are working with is part of the dataset. The easiest way to do that is by using Merkle trees. Merkle tree is a data structure that allows you to prove that a single piece of data is part of a larger data set. And the commitment we saw on the line on the slide before was the top node of the Merkle tree, which is what we call a root hash. If you wanted to read the tree data in the smart contract, this is when things become a little bit funkier because you have to do a lot of heavy lifting yourself. I won't go over everything in like super low-level detail, but what you would have to do is you would have to get a Merkle witness, calculate the root hash, then have a commitment or a precondition in the account updates to the root hash of the tree, which again comes back to the race condition problem that I was mentioning before. So as you can see, like the code required to just read data before you even start doing any computation on it, it's just like growing and growing, right? The same applies for writing tree data. You need to have like a lot of excessive boilerplate that you might not need if you use a different level of abstraction than smart contracts. That's what we'll talk about in just a minute. So, what are the design limitations? So we know that the contracts are executed on the client side. It creates race conditions, or like through the preconditions that we've been mentioning. How does this work? How does this work in terms of like a life cycle? So we have the same counter increment contract diagram we see that there's some data flowing in from some off-chain storage database. We have Alice executing the contract, again producing the account update list. And the account update itself is structured in a way that it has the preconditions to the hash of the Merkle tree that is storing our data. And it also has instructions for the chain to update the on-chain data to the new root hash that contains the data after the counter update. The problem is, if there's multiple people, not just Alice, they will have a collision on the precondition. And if you send 10 transactions like this at the same time, only one of them will be valid because the others will have the outdated precondition, while the new chain state has advanced to the new root hash. So, what can you do about it? Like, how can you use these low-level primitives to build applications that can work in the Mina ecosystem without having to worry about all of the infrastructure and all of the boilerplate code that we have just seen? The answer to that is a framework that we have built over the past several months called Protokit. It's a application chain development framework that allows you to build privacy-enabled application chains. So why are we even talking about application chains, rollups, or L2s when we have smart contracts? The important thing to realize here is that since the smart contracts are effectively executed off the chain, even the smart contract itself is de facto like a rollup that settles on a per transaction basis. So building an application chain is not so different from building the smart contract itself, just with the small difference is that the Protokit API is way more high level and way more similar to what you might be used to from ecosystems like EVM, and it's not as low level as the account update API and the smart contract. Getting started with Protokit is really simple. All you have to do is clone the starter kit. So what is Protokit? So it's a TypeScript-based framework for building application chains or ZK chains or ZK rollups. It is not using an EVM execution environment, so it's not another ZK VM. Instead, it's a custom-tailored ZK VM that allows you to write application-specific codes, making your chain a lot faster than running general-purpose EVM or any sort of general-purpose smart contract execution engine. Thanks to the fact that all Protokit app chains are also built as circuits, it allows us to offer a hybrid execution model. That means you can have logic that lives both on and off chain. The on-chain logic is going to be sequence, as you are already familiar with the EVM execution model. But thanks to the fact that we have recursive proofs, which we've talked about earlier, we can also do off-chain execution. So we don't lose any features over the smart contracts, but we have the extra feature of the on-chain execution that allows us to combat the precondition problem that we had with account updates. So the off-chain part also allows us to preserve privacy, and that is what makes the application chains privacy enabled, because you can do computation on top of private data on your client in your browser, take that proof, not expose any sensitive data about the computation you have done, send that on chain to a Protokit app chain that you have built for yourself, and get that sequence, get that verified, and recursively include it into an L2 block. The entire execution of your Protokit application chain is end-to-end proven. That means that whoever is operating the sequencer for your chain, which is possibly yourself, won't have any room for any malicious behavior. When it comes time to settle your state to the L1 itself, the L1 can then take the resulting block proof and verify that you have done all of the block production, transaction inclusion, and everything else that was required the way you were supposed to. Same as with the counter example. The framework is built to be customizable and modular, so if there's a feature that you don't like, or you would like something to behave differently, you would like to use a different database for your sequencer, you want to have a different mempool implementation, it's super easy to do, and it was designed to be completely modular. We also like to claim that there's virtually no learning curve, since we assume that everybody is familiar with execution environments like EVM. Doesn't mean we shouldn't pay attention though. So, all right. So, how can you build your own zk-rollup? So, zk-rollups, as I've said before, it's just the collection of recursive zk circuits that come together to produce a block. So you have circuits for your business logic. So that would be like whatever on-chain logic you need to have on-chain, like for example, balance transfers, NFT transfers, auctions, governance, or whatever else. You would implement that within our framework as circuits. The L1 itself also has some primitives that help us with this. We can do something called based sequencing. That means that we can use the L1 as a mempool, and that helps us alleviate things like censorship concerns thanks to the L1 consensus. It's important to say, like, you can really roll your own zk-rollup in a matter of a few hours, and that's what I'm hoping to see during this hackathon. And I've covered this before, but zk-rollups and Protokit chains are really a superset of zk apps or the smart contracts you've seen before, with the benefit of also having sequenced on-chain execution without the precondition issues and the difficulties of Merkle trees. We've abstracted all of that away behind what I think is a really nice API, and I'm hoping that you'll have fun using it during the hackathon. So what is a Protokit application chain or a zk-rollup made of? You have three main parts. You have your runtime. That is where your application logic would live. Think of it as smart contracts, but since this is an app chain, we don't call it smart contracts. We call it a runtime because it's the heart of your rollup. Next part is the protocol that contains all the circuits required for the underlying VM. That would be block production, handling transaction fees, handling account state, handling something that we call state transitions, and many other like low-level things that you don't need to care about anymore because we wrote them for you as part of the framework. And then you have the sequencer, which is, let's say, a centralized server, quote unquote, that orchestrates all of that for you, helps you operate the mempool, helps you deal with the settlement of your chain and the chain state to the L1. And the only thing you have to do yourself is pretty much only the runtime. We have 2 minutes left, so let me just hurry up through all of these slides. There's a bunch of really interesting features. You have bottomless on-chain storage, not like with the smart contracts. You can focus on the business logic because we wrote all the infrastructure for you, so you can just reuse it. It's integrated very well with the ecosystem wallets, so you don't have to really worry about that. And you can provide a really good user experience as part of your UIs. I've already said it's not another zk-VM, but a custom succinct zk-VM. Let's go on. So this is roughly how the lifecycle of a transaction on a Protokit app chain looks like. So at the bottom part, this is the most important. You don't have to do any proving on the client unless you want to. That's the top left corner. All you have to do is sign a transaction that's going to be a lot faster than proving it on the client. You send that to your zk-rollup, to the sequencer, and then the sequencer is the one executing the actual circuit logic and doing the proving server-side on much beefier hardware that you can ever carry in your pocket. That's like the whole point. The separation is runtime logic produces not account updates, but state transitions. These are applied through separate circuits, and you end up again with a block proof. And that block proof, it's like one huge account update that goes to the Mina L1. This is how you can write the runtime. It's relatively simple, and it's very similar to the smart contract API. This is how you would, for example, implement your own ERC20-like balances runtime. You can get the balance for the from and to addresses. You can do some business logic, make sure that you have sufficient balance, write your own assertions, then subtract the balances and update the balances in the state. So this is pretty much all you have to do. And it's very similar to like what you would have to do in like Solidity. Testing it is also very easy. As part of the framework, we provide like testing primitives that make it really easy to iterate on top of whatever you are implementing. And it also like pretty performant. The tests are relatively fast and so on. Executing the transactions either in your tests or in your client is also very simple and very similar to the original Mina API. I guess you get the picture. We offer GraphQL APIs and programmable query APIs that you see at the bottom. Makes it really easy to fetch the state as well. All you have to do if you want to compete for the Mina bounties at this hackathon is get started with the starter kit. You have to clone the repo, install the dependencies, start the sequencer, start the example UI, and start hacking away on your own logic. This is what you get out of the box, like a sample UI, connects to the wallet, produces blocks, and lets you interact with the local faucet. This is not that important. And yeah, thank you for listening. If you want to learn more, go to our website, protokit.dev, or find me around at the Mina booth, and I would be more than happy to help you with your hackathon project. Thank you again.